P and Q. So if no observer is able to detect cloning, then perhaps we can make a way about paradox. Now we have some refinements that I will present now, which make this problem, which challenge the idea of complementarity. And one of them is based on an observation about the properties of quantum entanglement of fields near the horizon. And so this is called the strong relativity paradox, and it was first formulated by Samir Mathur in 2009, and then it was elaborated by and expanded by us, who called it the Feynman paradox. So let me briefly explain the paradox. So yesterday we discussed the entanglement entropy of the Hawking radiation as a function of the number of particles. And we found that according to the computation of Hawking, the entanglement entropy keeps increasing forever, and at the end of the evaporation we have a mixed state, while according to unitary evaporation we expect that the curve will have this form. So, in order for this to be true, what it means is that the particles which are emitted after the half point of evaporation have to be entangled not with a remaining black hole, but rather with the Hawking radiation which was emitted in the past. So, let's draw a black hole here, and we have the radiation which was emitted a long time ago. Let's call it A. So this is the Hawking radiation which was emitted in the past, and we consider a new pair of Hawking particles produced near the horizon. One of them we call B, it's the outgoing particle, and this partner is called C, the ingoing particle. And what I'm trying to say is that if we have after the point of half the evaporation of the black hole, this particle B will have to be entangled with A in order for the entanglement entropy of the Hawking radiation to be decreased. If this B was entangled with the black hole, then when this particle B joins the remaining Hawking particles, the entanglement entropy of this radiation will increase. Instead we want to go down, which means that this particle has to be entangled with the early Hawking radiation. So for this part of the diagram, and for unitarity, we need that B is entangled with A. Let me also draw a thinner diagram to make clear what I'm talking about. So this is the Hawking particles which were emitted in the past is what we call A, and we're considering a new pair of Hawking particles, B, C. And what we're trying to argue is that when this guy B travels, the of this particle starts to decrease, because we're on this part of the curve. We have assumed that the evaporation is unitary, so the entanglement entropy has to decrease. So if we want to quantify a little more, we can say that if we consider the entanglement entropy of A together with the particle B, it has to be less than the entanglement entropy of A alone. And this has to be true after the half point of evaporation. So this is what we need for unitarity, right? Is this point clear? Are there any questions?
You say it should be true only after half point, but should it be not somehow true from the very beginning? Or the curve is always lower than the true of the
Well, this notation means that you take A to be a particular point, let's say this point, and then you add one more particle. So this is point A, and this is point A together with a new particle B. So if you're on this part of the curve, SAB is greater than SA. If you're on that part of the diagram, this is A, and now we're adding one more particle, and we move there, so this is A together with B. Now the entanglement entropy has to decrease. Yeah.
There are these soft gravitons which were all in the papers like very strongly on Hawking and so on. Are they included somehow in your consideration? Or?
Yeah, I mean, if they exist, they definitely have to be included in order for the final state to be true, because you would expect that these particles will be entangled with normal Hawking particles. So if you want to check unitarity, you have to consider all particles which are produced by the black hole. So we would have to include them, yes. I think that in the paper they mostly talked about the entropy of the black hole, if I'm not mistaken.
The argument that the whole entropy so can be encoded in soft modes, right?
Yes. No, I'm not sure if they make any statement about the information paradox.
That's right.
Yeah. Okay, so after the base-time, we expect that this particle B has to be entangled with an early radiation A. It's important to notice that we're not saying that this particle B will be entangled with one particle of radiation. So the entanglement is not a pair of particles. This particle B is entangled with the entirety of the early Hawking radiation. So if you take only two, if you take this particle B and the particular particle of Hawking radiation, you compute the mutual information between these two, it's going to be exponentially small. So this particle is not significantly entangled with any particular particle of radiation, but rather it is entangled with this entire system. As I said before, you can check this by using a model, for example, the spin chain that we discussed yesterday, where you can check out these properties explicitly if you want. Now the problem is that we have this entanglement between B and A in order to restore unitarity, but at the same time we need entanglements between B and C if we want the horizon to be smooth. So for the smoothest horizon, we need that B is entangled with A, sorry, with C. So this way, I think yesterday Raphael and Lars discussed this in the context of range space. So if you take class space and you divide it, the problem feet, you find that the modes on the two sides of space, if you divide space by introducing these radial horizons, you consider the Minkowski state and you expand it in a basis of modes corresponding to the right and the left waves, you find that the Minkowski vacuum is an entanglement state. And in particular, if you concentrate on the mode of given frequency, you find that the entanglement is of the form sum over the expectation levels of the mode, e to the minus pi omega n left and right. And of course, you have to take the product of all modes. There's an infinite number of those, so you have to be careful about that. But the point is that the Minkowski vacuum is a highly entanglement state between the right and the left. Now, this entanglement is actually necessary in order for this horizon to be smooth. What do we mean by that? This state is the unique state in the quantum field theory with a property that the stress tensor, T mu, is equal to 0 everywhere. So there's no excitations anywhere in the quantum field. So an observer who is crossing this horizon will not notice anything. If you modify the quantum state by modifying this entanglement, generally you will introduce energy to the system. So T mu is not going to be 0 anymore. So if we modify the entanglement, so if we reduce or modify the entanglement, between the two waves, then we generate excitations. So we're no longer in the ground state. That's pretty obvious, right? This is a unique state. The ground state is unique. If you change the state, you will have a state with excitations. But you can also check it explicitly in a free field by writing down some modification of this entanglement and calculating the stress tensor on the new states. And from that you can compute what will be the distribution of energy of space-time. So an extreme possibility would be to consider a quantum state where we demand that the field looks like the vacuum on the right, it looks like the vacuum on the left, but there's no entanglement at all between the left and the right. How do we do that? Well, if it is a Minkowski vacuum, and if we trace out the left part, we generate the reduced density matrix for the right waves. So we start with a Minkowski vacuum, and we trace out the left part, and this generates the density matrix for the right waves, which, as you know, is a thermal density matrix with respect to the Hamiltonian, which corresponds to the boost. That is the Moore effect, right? The same is true for the left waves. So now suppose that we take density matrix of the total system, which is the tensor product of the left and the right. So there's no entanglement now between the two wedges, but each one of them, locally, for experiments that you do only inside the wedge, it looks exactly like a vacuum. Then we will be in a situation where the space-time looks like the vacuum here, it looks like the vacuum there, but there's no entanglement between the two wedges. And if you take that state and if you calculate the stress energy tensor, the expectation value of T mu, you will find that it's 0 everywhere inside these two wedges, but it blows up once you try to cross this horizon. So this shows that whenever we have space-time and we cut it in some region into two parts, if we want the space-time to be smooth in that region, then we need to have entanglement between the two sides. Now, this calculation can be done easily in the black hole in a flat space, but you can do a similar calculation locally near the horizon of a black hole, and the qualitative conclusion is the same, that you need to have entanglement between the modes of the quantum field on the two sides, if you want that an infrared observer does not detect any excitations on the horizon. So what this means is that when we consider the black hole evaporation and we have a new pair of vacuum particles produced near the horizon, then if we want the horizon to be smooth, we need these two guys to be highly entangled. So here we have a problem because we have found we have two different conditions about this particle B, that B has to be entangled with C, its Hawking pair inside the black hole, and at the same time B has to be entangled with the early Hawking radiation, and this violates a property of quantum entanglement, which is called monogamy, so this violates the monogamy of quantum entanglement. So the relevant system is the particle B. Now we can make it a bit more precise by using a property of entanglement entropy, which is called strong subadditivity. So let me write here.
The black hole situation seems to me at least a little bit different from the Rindler situation. You entangle between the left and the right wedge.
Yeah. Oh yeah, yeah.
Not across the
Sorry, I did not.
You entangle across the right.
Yeah, I did not. I should have explained it more. So again, let's look at the Rindler space. When an observer crosses the Rindler horizon, what is relevant for this observer is the entanglement between the modes that are on this side of the horizon and the modes that are on this side of the horizon, as you say, right? The entanglement of this guy will be measured. But these modes, if you trace them back, they're coming from the left wedge. So if you want these guys to be entangled in this region, they should have been entangled already when they were here. Here.
That's on that side, that's one side is now, but this is
Yes, yes. In this case, the right wedge and the left wedge, basically, if you have access to the right and the left, you can reconstruct the future and the past, right? They're not independent. They do not correspond to independent factors of the Hilbert space. Anything here can be fully reconstructed by the left and the right wedge. Okay, so let me now go to the strong subadditivity. So the strong subadditivity property of entanglement entropy is a statement that if we have three independent systems, so we have A, B, and C as independent quantum systems, by which I mean that the Hilbert space can be factorized as a tensor product of the three Hilbert spaces. Then the entanglement entropy of, you can consider the reduced density matrix in all possible combinations here. You can take A together with B, A together with C, and so on and so forth. And then the entanglement entropy has to be this inequality. Alright, so let's apply apply this theorem to the situation that we have during black hole evaporation, where A, B, and C is what I have indicated over there. So, as we explained, if we want the horizon to be smooth, then B has to be highly entangled with C, and in particular, if you take B together with C, they have to be in a pure state. How do we see that? We can see that in a linear space, where we wrote down the expansion, and you notice that you have a left and right modes, but if you take this, a left mode and its partner on the right together, they're in a pure state. So these guys, if you take them together, they're in a pure state. So SBC is equal to 0. However, we know that S of B is order 1. It's not 0, because the particle P is a particle which is thermally populated. Right? So together these two guys are in a pure state, but B alone is in a thermal state, which means that C will also be in a thermal state. Since B and C together are in a pure state, the entanglement entropy of B will be equal to the entanglement entropy of C, right? So we know that this is of order 1. So one particle, this is 0, and then this inequality is telling us that SAB has to be greater than SA, which means that it contradicts what we need in order to restore unitarity. So this is telling us that the entanglement entropy will have to keep increasing forever as we add more and more particles to the Hawking radiation. Right? All right. Now, of course, you can have some objections here. You can say that maybe these statements are not exact. Maybe there's some small corrections. So maybe this entanglement is not exactly 0. Perhaps these small corrections can fix the problem. But Samir Mathur has proved the theorem that small corrections cannot fix this problem. So I guess he will review it in one of his lectures later this week. But let me say that that theorem relies on certain assumptions about locality, which I'm going to address later. So what I want to say is that if you relax some of the assumptions of the theorem, it may be possible to avoid it, I think. Yeah. If you have a system, so is this clear? First of all,
you're assuming that they're in a product state.
They're together. They're in a pure state. Not a product state. It's together. B and C are in a pure state. That's what we get, for example, in cosmic space.
SBC means you have traced out part A.
Exactly. And I'm saying that if you trace out A, you find a pure state of the subsystem B together with C. Good. So this means that B and C are in a pure state. So if you have a system, a quantum system with certain parts, B and C, and if you know that the full system is in a pure state, then it's a theorem that the entanglement entropy of this guy is equal to the entanglement entropy of that guy.
Okay. Yeah. We're now just talking about B and C, not A.
Yes, and I'm doing that because I can do that because by this assumption I have concluded that B and C together are in a pure state, so I don't need to worry about A. I could have A here, but I'm not going to use it for anything.
No, how B is entangled with A and C is entangled with A. This is what I'm saying.
No, I'm saying from the computation of Hawking, I get this result, which is telling me that B is not entangled with A, and C is not entangled with A. Instead, B is entangled with C. That's what Hawking's computation is telling us. But this is a contradiction with what we need in order to restore unitarity. Okay, so we have this paradox, and then the question is, how are we going to avoid it? Are we going to give up one of the two entanglements, the one that we need there or here? So, of course, if you assume that there's no entanglement between B and A, then you go to unitarity, and we're not going to talk about the possibility. The other possibility is that, for some reason, this is not correct, so there's no entanglement between B and C. But as I explained a little bit earlier, if you do not have entanglement between B and C, then you will generate particles on the horizon. There will be physical particles that the influent observer will be able to detect. And the problem is that if you do that, if you run the same argument for all modes of the quantum field, not just one of them, but all of them, then you will generate a huge number of particles on the horizon. And if you have this very large number of particles, will generate a very large density tensor on the horizon, which will back react, and it will completely modify the geometry. So if you give up BC entanglement, then we generate energy on the horizon particles. And this may lead to modification of geometry and it may lead to something like a firewall. So a region of very high density near the horizon, which will modify the geometry, and perhaps there's no interior. Yes.
Maybe you're going to address this, but that's assuming that the is basically broken when the modes are very close to the
of course, I was planning to mention it, but another possibility that Steve has discussed is that it could be that when this particle B is produced near the horizon, it is entangled with C, but then as it travels out towards the area radiation A, then at some point the entanglement between B and C is broken by some non-local effects. Is that what you're talking about?
Yeah, I think it's my whole picture.
Yeah.
One other comment related to that, the Hawking radiation really is, in a sense, produced when the modes hit a wavelength when they escape to a distance comparable to the black side from the black hole. Like, there's a sense in which that Hawking would become real.
Yeah. So I should emphasize that this is a short paradox if we insist on having exact locality, or that we do not have any non-local effects in the exterior of the black hole. Yeah.
Sorry, I guess I want to understand on this. I would say that as long as we have operators that can access the quantum information in those modes, they are as real as anything can get, and those operators are certainly available. Is that generally close to the black hole? How would it be?
This also proves you have a risk horizon, and we know there's no production of
ADS version of the paradox, I will probably come to your point, which is that we can try to, if we try to find operators which represent the region, the most near the horizon, we will run into paradoxes which are not exactly this one, but quite similar. So for a big black hole in ADS, there is no operation, but as we will discuss later, there is a problem in reconstructing this mode BNC from the boundary. Okay, so if we give up this entanglement, then we have this dramatic prediction that the black hole horizon has been modified, and let me emphasize that this is a big effect over macroscopic scales, because it would apply to a black hole of arbitrary size. So in particular, it would be relevant for a black hole of very large mass, where the curvature at the horizon can be quite small. So this will be a modification of GR in a regime where we wouldn't expect this. Okay, so before I move on to ADS-CFT, let me mention one more aspect of this paradox, which is that, well, yesterday we discussed about the idea of complementarity, black hole complementarity, which is that perhaps the quantum state on the night slice does not make sense, and that's why we said maybe we don't need to worry about cloning. So you could have asked the same question here. If the quantum state on the night slice does not make sense, then why do you try to apply the strong subjectivity inequality on that slice, right? Because that's what you're doing. We're considering this nice slice, and we're saying that three quantum systems, A, B, and C, and we're applying the strong subjectivity theorem to them. But according to the principle of black hole complementarity, we should not be doing that, because maybe there's no well-defined quantum state on the slice, right? However, and again, the logic is that there is no observer who can actually measure or detect the violation of strong subjectivity, right? That would be an argument. Who can detect this violation? Well, actually, it is possible to detect it, and that's what was pointed out by Amps, and I guess Raphael maybe explained more detail at this point. In the original paper, yeah, it was actually the original paper to some extent. So the idea is the following. We consider the black hole operation after the space-time, and this particle B, according to, if we want to have unitary operation, this particle B has to be highly entangled with the L radiation. What this means is that you can identify in this Hawking radiation a tensor factor, let me call it B tilde, which is maximally entangled with this qubit B, with this mode B. So this B tilde represents a scrambled mode which is encoded in the entirety of the Hawking radiation, and it is what purifies the mode B. So these two guys are maximally entangled. At the same time, for the surface of the horizon, we want B to be maximally entangled with C. So what you can check is that it is possible for an observer to go through the Hawking radiation, extract the scrambled qubit B tilde, and then dive into the black hole, where this observer will encounter both B and C. So this observer is holding the tilde, and he's carrying the tilde with him as front of the black hole, and then it takes B and C. So there is a single observer who can detect all those three particles at once. And if we assume that we have maximal entanglement between both B and B tilde, and between B and C, this observer will detect a violation of monodromic entanglement. So there's some thought experiment that you can do in principle, which will be able to detect this paradox. Of course, there's some interesting discussions whether it is extracting this qubit is extremely difficult. So an interesting question is whether there's enough time for this guy to go through this Hawking radiation, extract the qubits, and then jump into the black hole. So there have been some interesting discussions about that, but I'm not going to go there now. Okay. So that's what I want to say about the paradox of flat states. There's a question?
So the speed field effect is probably the fall of A, right? Like,
no, it's a tensor factor. I mean, A is a very big Hilbert space. It's a very large Hilbert space, right?
Right, but can really some hypothesis that for any given part of the field, like it's really completely different, right?
Yeah. So what I mean is, you can take this big Hilbert space A and select the basis in a clever way so that you get B tilde as a small tensor factor of the Hilbert space and the rest, and then B will be entangled with B tilde, right? But of course, to do that, it is extremely difficult, and in particular, the result will depend on the particular black hole that you consider. I'm not saying that a fixed tensor factor of A which is always entangled with B. Yeah.
Right, from the argument you see that particles to your right entanglement.
Well, I said that if you break this entanglement for a large number of particles, I mean, we run entanglement for one mode now, right? But we have,
for example, this error is a large number of particles, so the error of this room.
Well, you can just do the calculation by taking flat space. You can do the calculation locally, right? So you can use flat space as a toy model, right? And take this state there and break entanglement for like a very large number of modes and compute the stress tensor. If you do that, you find that it has very high energy. Before I go, let me mention a technical point here that if we want to have a smooth horizon, it's not only necessary to have entanglement between the two sides, but we also need to have a specific form of entanglement that I wrote down. That's why I wrote here that if we reduce or modify the entanglement, then we generate excitations, right? What I mean by that is that if you take the Vygotsky vacuum in flat space and you modify the details of the entanglement, for instance, if you introduce a phase here, which depends on the occupation level n, if you do that, the entanglement entropy does not change. So this new state is as entangled as the previous state, but the details of the phase of the entanglement are different. Now, if you compute the stress tensor of this state, you will find that it's not equal to 0. So you do generate excitations by changing the details of the entanglement. So what I want to say is that it's not only that we need B and C to be entangled, they have to be entangled in a very specific way. Okay, any other questions about the paradox of flat space before I move on to ADS-CFT? Okay. Now I don't know, how many of you are somewhat familiar with ADS-CFT correspondence? Okay, so I will assume that you have seen some introduction before, but if you have questions that I can try to answer them. But let me give a very brief overview. So the idea that we have ADS-CFT is that we have a conformal field theory, living in d dimensions. So we have a CFT, d-dimensional CFT, equivalent to quantum gravity or string theory on AdS5, AdS d plus 1 times some internal manifold.